All right, guys, are there any questions on any of the homework assignments? If there are no questions on the homework assignments, we'll go on and start today's lesson. Now, the first part here, find a number when multiplied by itself, you get a negative number. Now, we've already talked about this a little bit yesterday because when we tried to find the square root of a negative number, it didn't work. So, an example of this would be, say, 2 times 2. Well, 2 times 2 is 4. Well, positive times itself is still positive. If we take negative 2 times negative 2, we get positive 4. It's still, but the concept is still the same. We still end up with a positive number, yes? So what we're really trying to get at is we have to really, let's say we imagine a number, let's call it I. When multiplied by itself, when it's squared, we equal a negative number. Because that's really what we're trying to get at, is what number times itself would be negative. Well, if we square root both sides, we're really saying that our imaginary number would just be the square root of negative 1. And that's actually what it is. I is defined as the square root of negative 1. I does show up in other places dealing with vectors, but then it's dealing it in a different case. For us here, for our solutions, I is going to be the square root of negative 1. It is going to be our imaginary numbers. Now, imaginary numbers do show up in a lot of places. The main place that they do show up is in technology. A lot of stuff dealing with electricity. Because if something is really dealing with the fact that if there is the possibility of current or possibility of something to work. Now, most of those calculators that are still over there that no one is using right now are turned off, yes? So the motherboard that is inside the calculator, is there any electricity running through it? So mathematically, when they set it up and actually write the systems for it, so we know what kind of capacitors and battery we need for it, we need the equations for it. Those equations also have to take into the account when it's set up with the electricity flowing through it and when it is not. And that's really where imaginary numbers come into play, because we can write the equations and have them set up to where it is true and it holds true for the equation when there is no electricity flowing through it. That's where our imaginary numbers come into play, when there is no current flowing through it, but it still has the potential for it. And as soon as it's switched on, it comes out of dealing with the imaginary numbers back into the real numbers, and it can switch back and forth. So electronics is a lot of the times where imaginary numbers do come into play, and we deal with those. But we'll be using them to solve equations. Now, we won't deal with solving equations with imaginary numbers right yet. We're just going to deal with the imaginary numbers themselves. So the first thing we're going to deal with is simplifying the square root of negative 25. Well, let's break this up, because this is the same as saying negative 1 times 25, which is the same as negative 1 times the square root of 25. Now we know that what the square root of 25 is. The square root of 25 is 5. Now what did we just say the square root of negative 1 is? So the square root of negative 25 is 5i, because I, by definition, is the square root of negative 1. Now, I won't always show up like this here with a curl. It's for imaginary numbers when they deal with I, it's going to have that little curl at the bottom, or it's going to wear a hat. It's literally, I think of it as wearing a hat because it has that little arrow above it. That is another way they will signify the imaginary number I. But this is it. So really that I came out of the fact that it was negative 25 and not just 25. Any questions on this here? Now when we look at this next one, the negative inside the radical is going to turn into what? It's going to turn into that I. So what we can say is I can go on and simplify that down to I, which just leaves me with the square root of 72, because the I is the negative part. Yes? Any questions on this here? Now, we could type the square root of 72 into the graphing calculator, and it's going to give us a decimal number. Yes? Try typing the square root of 72 into the yellow calculator. Yes? So the negative part of the inside of the square root, because I is the square root of negative 1, yes? So that means this negative, when we fully simplify it, will be I. So we can pull that out. So really writing I out there is pulling out that negative, which leaves us with the square root of 72. Can we simplify the square root of 72 in the yellow calculator? Yeah, so if we type it into the yellow calculator, it tells us what? 2, and it would be 6i squared of 2. Because the yellow calculator will not deal with imaginary numbers. It's out of its programming, it can't do that. Now, it does work out the graphing calculator can do the negative square roots. We'll show you here in a minute how to get it set up properly, but it doesn't simplify radicals. The graphing calculator can deal with I, but won't simplify radicals. The yellow calculator will simplify radicals, but it can't work with I. It can't take the negative square root. But, wait a minute. For this here, what did we do? We just, okay, since it's negative inside the radical, the negative's going to come out as I. Then the yellow calculator can simplify the square root of 72. I mean, we just dealt with the I part and let the calculator do the rest, yes? Now, negative 5 times the square root of negative 9. Is 9 a perfect square? Is there a number that times itself as 9? 3, yes? So that radical will simplify completely. We don't have to worry about, say, a square root of 2 like the last one. So what we can do is we can pull up the graphing calculator and say negative 5 second square root, negative 5 second square root negative 9. And when we hit enter, it tells us the answer. Well, in what kind of mode? Real. Is the answer that we're going to get going to be a real number? Well, it's going to have what part? It's going to have a imaginary part, so it's not real, correct? Now, mode, if you click on mode, right down here it says real, because I had it selected. I've already reset this twice today, so it's set up here. Because right now, the way I have this calculator is set up in real. It's only going to deal with real numbers. Now, if we move over to A plus BI and hit enter, it is now set up to deal with imaginary numbers. It will take the root. I just have to switch it over from real to A plus BI. Okay? So that means in the spring, when y'all take the ACT again, I'm going to end up resetting the calculator so that nothing gets brought into the testing site and we have to reset them so nothing comes out. Well, if they get reset, what mode is it going to be in? Real. It's not going to be in the A plus BI. So that means if you're doing this, you'll have to switch it over from real to A plus BI to take the square roots of negative numbers. Or we could pull the negative out as I and use the yellow calculator and it would do it for us. Does that make sense? Because we could do it the other way also. So if I hit enter, we get it there, second quit. I can tell it to do it again. Enter. And it tells us it's negative 15i. So it will do it for us. A plus bi. Because the A, the real part, because A plus bi, A is the real number, bi is our imaginary. Here, the real part, the real number is 0, so it's 0 minus 15i. But we can just write it as minus 15i or negative 15i. Because if we did this by hand, we would have negative 5i, because the negative coming out of the radical would be I. Square root of 9 is 3. Negative 5 times 3 is a negative 15i. And that's it. Any other questions on this here? So really, it's just pulling that negative out and then simplifying the radical. So the square root of negative 4, well, the negative would come out as, I'll second, because the square root of negative 4, well, the negative would come out as I, and the square root of 4 is, so the square root of negative 4 is 2i. And that's it. How about the square root, or negative square root of negative 36? So the negative out front would stay there. The negative inside the radical would become I. And the square root of 36 is? It would be negative 6i. Questions on any of this here? Do we feel comfortable with this here? As we're just pulling the negative out, simplifying everything else, yellow calculator can do it for us. We good with this here? Okay. Powers of I. Now I, these imaginary terms, cannot have an exponent greater than 1. I cannot have a power or an exponent greater than 1. Yep. Powers of I. Yeah, I mean, there is a book on I. I ordered it in college and didn't get it. They sent the wrong book. I got the history of the Habsburg Empire. They're one of the most one of the most powerful empires right there after the Roman Empire. And I asked Amazon and kind of got in contact with them, like, hey, I got the wrong book. They're like, okay, we'll refund it to you. Don't send it back. I spent $3 on it, so, and I think that was with shipping, so. But here, we've already said I is the square root of negative 1. Now we won't really be writing the square root of negative 1, we'll just leave it as I. Now I squared is really just saying that we have the square root of negative 1 squared. Well, the square root and the square would, leaving us with just negative 1. So I squared is negative 1. Well, I cubed would be the same as I squared times I. Now we're breaking this up because we already found I squared, yes? I squared is? So we have negative 1 times I, which is just negative. So we have negative I, because negative 1 times I would be negative I. because we can leave it as I. We just can't have I to a power, to an exponent greater than 1. So that's fine. So I, then I squared is -1. I cubed is -I. Well, I to the 4th, well, that's the same as saying I cubed times I. Well, I to the 3rd is -I. Well, -I times I would be -I squared. Now, what was I squared? So we have -1, which is just 1. Okay. Well, let's look at another one. Let's look at I to the 5th. Yep. This is going to be simpler than what you think. So we have I to the 5th would be the same as I to the 4th times I. Well, what is I to the 4th? 1. So we're saying this is 1 times I, which is so I to the 5th is the same as just I. Those are the same thing, aren't they? Okay. Let's look at I to the 6th. Well, that's the same as I to the 4th times I squared. Because I know I broke the pattern because we were doing the one before it. But what is I to the 4th? 1, yes? So I to the 4th is 1. What do I know about I squared? Okay, I to the 7th. Well, that'd be I to the 4th times I to the 3rd. Well, we said I to the 4th is 1. What is I to the 3rd? Anybody have a guess at what I to the 8th is going to be? It's 1. Because I to the 8th, we can say that's the same as I to the 4 times I to the 4th, which would be 1 times 1, which is just 1. Anybody else see the pattern that's starting to occur? Because what did we start out with? We started out with I. Yep. Because it went I, -1, -I, 1. I, -1, -I, 1. And it will repeat this pattern. And it ends up being the only 4 that we can have is it's going to either be I, -1, -I, or 1. Yes. And the interesting part of this here is for I to any power, if we take that exponent and divide it by 4, we're actually going to get one of these here. Because whenever we divide the power by 4, surprisingly enough, we'll get a number. Well, yes, we divide 2 numbers, we'll get a number. But we'll get a number point, a decimal. The whole number itself really isn't important. It's the decimal that is. The decimal is really what's important. Because again, it's going to be one of these 4, and it cycles around. The whole number is really telling me how many times through the cycle we went. We're really focused on where we are at the moment. Now, if the decimal, when we divide, is 0.25, it means that this reduces to I. If the decimal works out to be 0.50, it will reduce to -1. If the decimal works out to be 0.75, it would be -I. And what do we think the decimal for the last one's going to be? Zero, zero. It's going to be a whole number. So we do have that, and we worked through this here to kind of see how this works and the fact that it does repeat to give us these 4. But really, we can divide the exponent by 4 to see what we get. So I to the 27th. We're evaluating this here. We want to see what does this evaluate to. What we're going to do is we're going to take 27 and divide it by 4. We're going to take 27 and divide it by 4. What is 27 divided by 4?
75. Sorry.
You're good. 6.75. Now, we don't care about the 6 because the 6 is not important. What we want to look at is the 0.75. So which one did 0.75 line up with? So I to the 27th simplifies 2 down to negative I. That's it. That is it. Right, because we went through all the powers of I really to see, okay, there's only 4 possible setups that it simplifies down to. And that gives us this here. Now, so like I to the 34, we can take 34 and divide it by 4 and get 8.5. It really doesn't matter, it's the 0.5, which tells us this is negative 1. And that's our answer. So we have the other two, but let's look at 1040. And let's try plugging it in. Now to plug in I, we can go second decimal. Second decimal will give us I on the graphing calculator. So on the graphing calculator, if we go second decimal, exponent, 1040, and hit enter. Now the E is our times 10. So really what it's saying is 1 plus 4 times 10 to the negative 12th I, which in scientific notation is just saying that we have 1 plus 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 I. What is this number here really close to? 0, isn't it? It's just really close to 0. So what this is actually saying is that this whole number here is really that we have 0I. So it's 1. Now, erase that there. If we did it, the division, 1040 divided by 4, what is the decimal? There isn't 1, it's 0.00, so it means the answer is 1. It will give us the exact same thing. Now when we get those bigger exponents, it's going to have a slight rounding or pixel error because it's using the graph. And as we saw the other week, when we graph, it will have that a slight error. And that's what that is. And it can happen on both sides. So sometimes, especially with simplifying powers of I, it might be easier just to divide the thing by 4 than it is to try to figure out which one is actually 0 on the graphing calculator.
Mr. Brad, could you please come to the office, Mr. Brad?
Any questions on evaluating I? Addition and subtraction. To add or subtract two complex numbers, add or subtract their real parts and their imaginary parts. Okay, for adding and subtracting two things with imaginary numbers, add the parts without I, add the parts or subtract the parts with I, and you get your answer. 8 minus I plus 5 plus 4I. Well, since we're having addition or positive in front of both parentheses, we can just drop the parentheses, which tells us that we have 8 minus I plus 5 plus 4I. 8 and 5 are like terms because they don't have I, correct? So what is 8 plus 5? Negative I and 4I are like terms. They both have I, yes? So it's negative I plus 4I. That'd be positive. That's it. And we always want to write it in the form of A plus BI. We want the real number first. The number without I goes first. The number with I goes second. That's it. Questions on this here? Okay, next page. 7 minus 6I minus 3 minus 6I. Well, the 7 minus 6I, we can drop the parentheses because there's not any sign in front of them. But the 3 minus 6I, we do have to apply the negative through. So the 3 would be minus 3. The negative 6 would become plus 6I. 7 minus 3 is? Negative 6I plus 6I is? And that's it. Well, let's try that on the next one. So we have 13 parentheses, or 13 minus 2 plus 7I plus 5. So let's try plugging it in. 13 minus parentheses 2 plus 7 second I, close parentheses, plus 5 second I, enter. And that's it. So with any of the addition and subtraction, could we just plug it in? Yeah, the graphing calculator will do it for us. So 11 minus 2i. Because what do we have here? 13 minus 2 is 11. 5 minus 7i is negative 2i. Do we see another example with addition or subtraction? Well, the next thing we have is multiplication. So, with this here, to solve it, we would use distributive property. So we would say 4i times negative 6. Well, 4 times negative 6 would be negative 24i. 4 times negative 6 would be negative 24i. 4i times I is going to be plus 4i what? Squared, because I times I would be I squared. Now we can't leave I squared, but what did we say I squared is the same as? I squared is negative 1. That's one of the ones that will come up the most often. It's I squared. So kind of remembering that I squared is negative 1 can be helpful. Well, 4 times negative 1 is 4 minus 24i. I have a feeling some of y'all tried that in the calculator. Did you all get the same thing? Yep. Questions on this here? Let's look at this one. Nine minus 2i times negative 4 plus 7i. So could we plug this into the calculator? Yeah. If we did this by hand, we could distribute and distribute. 9 times negative 4 would be negative 36. 9 times 7i would be plus 63i. Negative 2i times negative 4 would be plus 8i. And negative 2i times 7i, negative 2 times 7 would be negative 14. I times I would be I squared. Now we said I squared is negative 1, yes? Well, what is 1 times 14? 14. It's not going to change it. Negative 1 is only going to change the sign, yes? So when I'm working these out by hand, what I would do at this point is I cross out I squared and change it from negative to positive. I'll just change the sign. If it's positive, I will mark out the plus sign and write a minus sign above it, just to signify that the sign did change. Negative 36 plus 14 would be negative plus. And that's it. Questions on this here? But I think some of y'all typed it into the calculator and got to the same thing. Yeah, the calculator will do this here. Any questions on this here? Are you good with addition, subtraction, multiplication? That is it for today. Division is tomorrow. I'm glad. Minus 12 is equal to, or on page 131, 6 through 12, 19 through 23, 32 through 38, even, and 44 through 50, even. So we will be looking at division tomorrow. And that is all we are doing to